Hello, everybody. My name is Kazim Oluwashino Amao, and you're welcome to my tutorial. Today, we're analyzing a simply supported beam that's carrying a triangular load, and our objective is to estimate the required area of steel. This is how we're breaking it down. Firstly, we'll start by analyzing the beam to determine the unknown support reactions. Next, we will cut a section of the beam at a distance x from A and derive the bending moments equation at that section. Then we will substitute different values of x into the formula to calculate the bending moments at various points along the beam. With those values, we will plot a bending moments diagram to help us identify where the maximum bending moment occurs. To find that maximum, we will take the derivative of the bending moment equation with respect to x and set it to equal to 0 since the slope is 0 at the maximum point. Solving that gives us the exact position x where the maximum bending moment occurs. We will then plug that value back into our moments formula to get the maximum bending moment. That maximum moment becomes our design moment, and finally, we'll be using this design moment to calculate the required area of steel. So without much talks, let's jump right in. Calculate the required area of steel reinforcement for the beam subject to the loading shown below. We have the width of the beam to be 300 mm, the depth is 500 mm, it has a length of 6.5 millimeter. Characteristic strength of the concrete is 30 newton per millimeter squared, the effective depth 450 millimeters, and cover to reinforcement to be 30 millimeters. First of all, what we are going to do, we need to determine the maximum bending moment, which will act as our design moment. But before we get there, we need to analyze the structure, get our reactions. After getting our reactions, find the maximum bending moment. Then we can always use that as our design moment for getting the required area of steel. First of all, what we are going to do, solution, if we draw the free body diagram underneath like this, represent the load on the free body diagram. So I just like to represent the load. So that's free body diagram for the structure. That's a triangular load. We need to find the equivalent point load for the 45 kilonewton per meter. So we need to convert that to equivalent point load. So converting 45 kilonewton per meter, converting into equivalent point load. So it's simple. Half base times height. Half big area of a triangle. Half base times height. So that will give us half times base of 6.5. That's the distance. Times the height. 45 there. So when we solve that, you get 146.25 kilonewtons. So the equivalent load, you have is something like this. It will act at 1/3 of this larger side. This is 6.5 here. So that will give you 2.17 meters. So here you have 4.33 meters left here. So having done those, we need to find the unknown reaction. We have our HA, our VA, our VB. So when you look at this structure, it's statically determinate. That means we can actually get these reactions from three equilibrium equations, which are summation of f of x is equal to 0, summation of f of y is equal to 0, summation of moment about the point is equal to 0. First of all, let's solve for the vertical reactions. So when we say summation of f of y is equal to 0, upward positive. So what is that? We have vertical reactions VA, right, plus VB, then minus 146. 146.25, they should equal 0. So when you do this, VA plus VB is equal to 146.25 kilonewtons. So we have two unknowns here. How are we going to go about that? Let's take moments about B. So from there, we should be able to get one of these reactions, then substitute it back into the, let's call this one. So when you say summation of moment about B is equal to 0, clockwise positive. So what do we have? 6.5 VA because it's positive. So that's clockwise. Then 146.25 kilonewtons, that will be negative because it's going anti-clockwise towards B. Minus 146.25 multiplied by the distance in which it's acting. So that's 1/3 of 6.5. So that's 2.17. 2.17 should give us what? 0. So from there, 6.5 VA should be equal to 48 when you solve that. 48.83 kilonewton. So let's substitute this back into equation 1. So what we have, then VB will give us what? 146.25 minus VA, which is now 48.83. So our VB will give us what now? 97.42 kilonewtons. We have our VB and we also have do we have our VA? Yeah, we have our VA. Obviously, HA will be 0 because summation of forces on the horizontal axis should be equal to 0. So taking this one to be positive, we have HA, that's plus HA. There is no reaction here because this is a roller. So there is no reaction, that's 0. So HA is 0. Now we now have all our reactions. We need to determine the maximum bending moment that is occurring on this beam. So what we are going to do to get that, we are going to cut a section through the beam. So at a distance x, we are now going to generate a moment formula in which we will now be throwing in different x values. With that, we are going to get different bending moment at different points on the beam, which we can use to get our bending moment diagram. And through that also, we are going to find our maximum bending moment, which we will then use as our design moment. Going forward now, let's cut a section at a distance x from A. This is a beam, so let's cut a section at a distance x from A. We've already found our reaction at A, 48.83. Yeah, we've got a section x meters, right? So let's say this is moment at x. As we have said earlier, we need to generate a bending moment formula in which we are going to throw different values of x along the beam. So we want to get the different bending moment values along different positions in the beam. We have a triangular load on it. This load to be acting at the point 45x over the length. And don't forget that we said it's acting 1/3 to this point. So this will be x over 3 meters. And when you subtract x over 3 from x, here will be what? 2x over 3 meters. So going forward, we need to determine a bending moment formula. So we can achieve this by doing what? Say, taking a moment about points. About these points here. So summation of moments about x is equal to 0. Clockwise positive. So what do we have? We have 48.83 multiplied by x minus. So this will be the intensity of this load. We'll convert it to point load, which will be half base times height. So doing that straight away, we have half times the base. Our base is x times the height, which is 45 x over L. Then it is acting at a distance x over 3 from here. So it's acting as a distance x over 3 from there. So that's a distance multiplied by the distance x over 3. What else? Then minus mx should give us 0. So going forward, when you organize and rearrange this equation, you will have, let me use another pen color for this. So you have our mx to be equal to 48.83x. Am I right? Yes, minus 7.5 x cubed over L. So This is the bending moment formula that we will use to find bending moment value at different x positions of the beam. Then we are now going to use the one that is maximum as our design moment. So because I have a total beam length of 6.5 meters, so I'll just like to have the bending moment at point 0, point 1, point 1.5, point 2, point 2.5, point 3, point 3.5, point 4, point 4.5, point 5, point 5.5, and point 6, then point 6.5. So those are the points on the beam where I want to know what the bending moment is saying. So if I say at 0 meter, so let's substitute x is equal to 0. Let's call this equation 2. In equation 2, so m at the distance x is equal to 0. So your bending moment is actually 0 around somewhere here at m. So we've done for 0. Let's do for 1. X is equal to 1. Okay, now we now have different moment values at different positions along the beam. So with this now, we can plot our bending moment diagram. So from the bending moment diagram now, you will understand how the beam is behaving. So now, as we said earlier, we need to know the maximum bend moment, which will serve as our design moment for calculating our reinforcement. We should know that the maximum bend moment will occur at a point when slope is 0. That means we will have our maximum bending moment around somewhere around here, where our slope is 0. So our bend moment will be happening somewhere around there. But we need to be precise. So what we're going to do, you should know that we can get that mathematically. Although you can look through all the values here and just pick the largest value, but we need to be precise. So we will be using whatever we get will still be close to the highest moments we get around here. But for precision's sake, let's derive that mathematically. So our bending moments will occur where the slope is 0. So now let's remember our moment formula from here. Mx is equal to 48.83x minus 7.5x raised to power 3. So now let's get the slope of this equation. So when we get the slope of the equation, we can now then equate it to 0 because we already said that maximal bend moment will occur when the slope is 0. Then from there, we can get the position at which bending moment is maximum. And then we can now slot that position back into the equation to get the maximum base moment. Don't get it twisted. Let's take it one step after the other. First of all, let's bring our moment equation. Where x equal to 48.83 x minus 7.5 x raised to power 3. That's our moment equation. So let's find the slope of equation. That means we will be differentiating with respect to x. So the moment of x over the x. So this is the slope of equation. When you equate this slope of equation, when you equate it to 0, you'll be able to get x value. You see that x value that you get, that is the point when you have your highest bending moment. Because we already said that the highest bending moment will occur somewhere here where you have your slope to be equal to 0. But we need to be sure, we need to have something precise. That's why we need to run through this mathematical expression. So let's go. So let's try and equate these to 0. You will have, so from here, when you solve these, you get, what this is telling us now is that our maximum bending moment will occur at a point x is equal to the root of 2.17 multiplied by L. So now let's get that. So x will now be equal to, we know that L is equal to our length of beam, which is equal to 6.5, right? So now we now have x to be equal to the root of 2.17 times 6.5. So x is equal to what? Let's solve this. X is equal to 3.76 meters. So maximum bending moment will occur at a point x is equal to 3.76 meters. So now let's slot back this value of x into our moment equation. So remember, what's our moment equation? So m, when x is equal to 3.76, so let's see, 120.3 is around where you can see it's around where we said, around this side, around this side. That's where the bending, maximum bending moment is happening. So now that we have our maximum bending moment, we use that as design moment in order to get our area of steel required. Okay, I hope you are understanding. Let's move forward. Now that we have our design moment, we need to find the ultimate moment of resistance of the section just to know if it's capable of withstanding the design moment. If you can remember, you know, our ultimate moment of resistance, RD, should be greater than our design moment. So how do we get that? We already know these are design moments. So now how to get this? Also, when you check for the K value, remember our design moment is 120.3 kilonewton meters, so you can convert that to Newton millimeters. And this is less than 0.160. So definitely, we'll be doing our reinforcement to be a single reinforcement. You can see our moment of resistance is way higher than our design moment. Having said that, we can move forward. We can now find our area of steel required since it's singly reinforced. So we really need to know our lever arm first. So let's solve for our lever arm. And remember, a condition must be met. We know our Z should not be more than 0.95D. So since we have it to be 0.94D, so we can just adopt Z is equal to 0.94D. 0.94 times 450, because our effective depth is 450, so it will give you 423 mm. So we can use that because it's not more than 0.95D. So now back to the formula for finding our area of steel required, right? Area of steel required. So and that brings us to the end of this tutorial. Let's quickly recap what we've done today. We started by analyzing the simply supported beam and calculated the support reactions. Then we took a section at the distance x from point A and derived the bending moments equation for the beam. After that, we substituted various values of x into the formula to find the bending moments at different points and use those values to plot a bending moments diagram. To determine the maximum bending moment, we differentiated the moments equation with respect to x, set the slope to 0, and solved for the critical position. We then plugged that x value back into the formula to calculate the maximum design moment. Finally, using that design moment, we estimated the required area of steel for the reinforcement. I hope this walkthrough has made the process clear and easy to follow. If you found it helpful, don't forget to like, share, or drop your questions in the comment section. Thanks for watching and see you in the next tutorial. Bye.